Welcome back, everyone, and thank you for coming back to the third of this lecture of the series. So in the last two lectures, so that means today, in the lecture next Monday, we will focus on the Erdös-Ginzburg-Ziv problem, which is the third part of this title. But we'll also come back to three-term arithmetic progressions and the slice ring polynomial method, because of course there are also connections to the things we discussed earlier. So in particular, we'll discuss today and next week whether and how the slice ring polynomial method can be applied to this problem. But let's start with the problem itself. So the Erdös-Ginzburg-Ziv problem is a problem in discrete geometry, and the statement of the problem is as follows. So given positive integers m and n, so m and n are given. The question is now, what is the minimum integer s depending on these m and n, such that among any s points in the n-dimensional integer lattice z to the n, so we are in this n-dimensional integer lattice, so all points in our n with integer coordinates. We're given s points s such points with integer coordinates. And the question is, how big do we need to make s so that then it's always possible to find m points with the property that their centroid is also a lattice point in z to the n. Okay, so we want to make s big enough, and the question is, how big do we need to make it depending on m and n, so that whichever points in this n-dimensional lattice z to the n we take, we are always able to find m points with the property that their centroid is again a lattice point in z to the n. The centroid doesn't need to be one of those s points, but it has to have integer coordinates. So just for completeness, the centroid of m points p1 to pm is simply the average . Okay, so if we have these points p1 to pm and zn, and we take their average, so we add them up and take divide by m, then usually this has real or rational coordinates, but we want to choose these m points in such a way among the s given points so that this average, the centroid, has integer coordinates. So in other words, we need to pick m points among our s given points so that the sum has all coordinates divisible by m, because then this average will have integer coordinates. Okay, so maybe because with pictures, maybe this becomes a bit more concrete. So let's take an example. So let's consider the example of n being 2, because the board is two-dimensional, so it's hard to draw anything on the board which is larger than two-dimensional. And let's take, so that the pictures don't get too big, let's take m to be 3. So that means we take some points in z squared, and we're trying to find 3 points among them whose centroid is again a grid point in z squared. So for example, here I drew 4 points in z squared, and among those 4 points I can actually pick 3. And I can pick this one, and this one. And then their centroid is going to be that point, which is a grid point in z squared, so that's good. So for these 4 points, that works. So among these 4 points, in z squared, it is possible to find m equals 3 points whose centroid is also in Z squared. Okay, namely I can pick these 3 points and then the centroid is here, that's in Z squared. So the question is now, is 4 points always enough? And if you've thought about it for a while, you might have if you think about it for a while, you might notice that that's not always enough because, for example, for these 4 points, it's not possible to pick 3 whose centroid is a lattice point. So, but for these 4 points, this is not possible. This is not possible. And so now the question is, how many more points do we need to take so that it does become possible to do this? And so if you play around with this for a while more, you'll see that even 8 points are not enough. So if you pick these 8 points, then you see that again you can't choose any 3 whose centroid is a lattice point. So this shows that even among these 8 points, it's not possible to pick 3 whose centroid is a lattice point. So this is not possible. Okay, and so now of course you can try to sort of look more, and actually one can prove that for 9 points it is always possible. So that means if we take n equals 2 and m equals 3, then this minimum possible S is 9. For 9 points it always works, and as this example shows, for 8 points it doesn't. So for n equals 2 and m equals 3, one needs S equals 9 points. So this example shows one needs at least 9 points, and that 9 points are indeed enough. One can show with a bit of a case distinction about where the points are. It's not terribly difficult. Okay, so of course that solves this problem for n equals 2 and m equals 3, but we don't care about this particular small example. That was just to illustrate sort of how this problem works and what we are looking for. Maybe the first remark is, but it's maybe not even a priori always obvious that there is such a finite S. But you can show with a simple argument that indeed there is a finite number S which is always enough. Because what we are aiming for is to find m points whose sum has all coordinates divisible by m. So we can look at the residue classes modulo m of the points. So in fact, that's sort of all that's relevant, right? Because this condition talks about the sum having all coordinates divisible by m. So in the end, only the residue classes modulo m of the coordinates matter. And so now, if we have sufficiently many points, namely something like at least m to the n plus 1, then we'll be able to, so that means m times m to the n, then we'll be able to find m many points which sort of all look identical if you look at the coordinates only mod m. So in other words, maybe to say it sort of a little bit more abstractly, if you project from z to the n to z modulo m to the n, you'll be able to find m points with the same image if you start with m times m to the n points, so m to the n plus 1 points. And so then if you find points with the same image, or in other words, points where the first coordinates have the same residue among all m points, the second coordinate has the same residue among all m points, and so on, then it's easy to see that the sum has all coordinates divisible by m. So indeed, there's an easy pigeon, so basically to just summarize that point, there's a relatively easy pigeonhole argument which I haven't written down yet, but just described in words, which shows that indeed there is such a finite number S. So the following definition is well defined. So this point is not super important, but I just wanted to add this to make clear that what I want to define now is well defined. So let's say the answer to this problem is denoted by S of z modulo m to the n. And so as this argument just showed, indeed this answer is a finite number. So indeed that's a well-defined number depending on m and n, and that number is defined to be the smallest possible integer so that this statement holds. And so now this notation S of z modulo m to the n might look a little bit strange at first, like maybe something like S of mn or something like that would be more natural. I think there's sort of different notations for this, but this notation is sort of very common because it reflects that, that this can be naturally translated into some problem in z modulo m to the n, namely a problem about sequences or multisets in z modulo m to the n, where you, I mean, as we already said, here it's only the coordinates of the points modulo m that matter, and so that means you can reformulate the problem in z modulo m to the n, and not to set up more notation, didn't want to rewrite the problem in z modulo m to the n, but that's sort of where this notation comes from. Okay, so yeah, so that's the notation, and so what this example then shows is that S of z modulo 3 squared is 9. So in that notation, that's what we get here. Okay, so that's the problem. Any questions about the problem, or is it sort of clear what the problem is? It's clear? Great. Okay, so then let me tell you what's known about the problem. Or let's maybe start more precisely with in which cases is the value of this, so the answer to this problem, actually known exactly. So here are the known values for z S of z modulo m to the n. So first, the value is known when n equals 1. So when the dimension is 1, then the value is known. It is known that it is S of z m to the 1 equals 2m minus 1. And this was shown by Erdös-Ginzburg-Ziv in 1961. And that's why this problem is named Erdös-Ginzburg-Ziv problem, because they solved it for n equals 1, and so they initiated this problem. Then for n equals 2, the answer is also known, but this actually took a long time since then. So the answer is known to be 4m minus 3 if the dimension is 2, and that's a result due to Ryer from 2007. So as you can see, that took quite a while. And for n equals 3, the answer is not known yet, so even for n equals 3, it's still open, but it is known if m is of a particular form. So for n equals 3 and m and certain m, and these certain m have only having prime factors in 3, 5, 7, 11, 13. So there are more conditions, but the condition is if you have an m which only consists of these prime factors and then with some additional conditions of the exponents, which are sort of complicated, so I won't write them here, then it's known that the value is 9m minus 8, and that's due to Fan, Gao, and Zhang in 2011. Okay, so in other words, for n dimension 3, the answer is known to be 9m minus 8, but only for a very special m with special prime factors. Then for n equals 4, the answer is only known if m is a power of 3. Then it's known that this is 20m minus 19. So that's due to Edel et al. From 2007. And then so these are all complicated things. One easy case is if m is a power of 2. If m is a power of 2 and n is anything, then it's known that s of the m to the n is m minus 1 times 2 to the n plus 1. And that was first shown by Harbord. But it's a relatively simple argument. So that was shown by Harbord in 1973. Okay, but so these are basically all the known values. So there's a few more known values where you pick a concrete small m and a concrete small n. But so these are up to finitely many sort of other small particular pairs. These are, at least to my knowledge, all the known values of this. And so as you can see from this list, most of the time the value is not known. So of course, when you have an extreme problem like that one, you can try to determine the value exactly. In some cases, as this list shows, this has been successful, but in most cases it hasn't. But another very natural direction you can try is you can try to estimate the answer. So you can try to estimate this and try to understand its growth behavior in m and n without wanting to pin down the value exactly. And so indeed, there has also been a lot of work in that direction. And so maybe let me write that to this board. Yeah, so we want to understand how this grows as a function in m and n. And so it's a function in 2 parameters. So a very natural thing is to first fix one parameter and then wonder how it grows as a function in the other. And so if we fix the dimension n and let m grow, then Alon and Dubiner showed that for fixed dimension n, this actually grows linearly with m. And that's sort of what these examples all show. So here, this sort of is bounded by from above and from below by linear functions of m. And so that's what Alon and Dubiner showed more generally for any fixed dimension n. So here's the theorem. Alon and Dubiner. And that's from 1995. And so they showed that for fixed n, so fixed dimension n, and large m, we have an upper bound for this Erdös-Ginzburg-Ziv constant. So this Erdös-Ginzburg-Ziv constant is upper bounded by a term of the form Cn times m, where the Cn is some constant depending on n. Okay, so we can upper bound this by a linear function in m, where sort of that coefficient is something dependent on the fixed dimension n. And of course, we also have such a lower bound for s of z m to the n. So s of z m to the n is trivially at least m, right? Because we need to pick m points, so we need to have at least m points. So that means that tells us that this grows linearly in m. Okay, so in other words, s of Cm to the n grows linearly with m when the dimension n is fixed. Okay, so now of course we can also ask, so what's this Cn that their proof gives? So their proof gives constant Cn, which is roughly n times log n to the n. I think there's maybe another constant here. So an absolute constant factor here. But yeah, okay, let me leave it like that. So it's something that goes roughly like n to the n. And so now that of course also raises the question, well, is that best possible? So it was shown, so basically this constant was improved relatively recently by Sakharov, but only in the case that m only consists of prime factors which are large with respect to n. So Sakharov sort of improved this for fixed n and when all prime factors of m are large enough with respect to n, so in this case, Sakharov proved that this is at most 4 to the n times m. So that's a really, really strong bound. So this bound is, I mean, that is already a very nice bound, but this bound is I mean, having such a constant factor here is really, really strong because there's a, which I'll say in a moment, there's a lower bound which is sort of a similar shape. So something like 2 to the n times m is a lower bound for this. And so that means this bound really sort of is of the correct shape because it matches the shape of the lower bound. Unfortunately, there's this little caveat that, well, if you fix n and you want to make m large, then sort of naturally you would assume n is fixed and m is large. Here you have to assume a little bit more. You have to assume that all prime factors of m are large enough. So it doesn't immediately apply this sort of for all large m, right? Because there could be a very large m which consists of small prime factors. Now, very small prime factors also don't matter, as we see in a moment. So in some sense, this is a bit of a technical caveat. So sort of very small prime factors won't sort of really mess with this. But maybe there could be medium-sized prime factors which are not sort of small and which are maybe bigger than 4 to the n, but not large enough for the large enough. So due to this assumption, this doesn't sort of literally always give this bound when we would want it, but it's sort of pretty close. So yeah, and so quantitatively, this bound is really very good. So let me say that now. So this is a very strong upper bound. And is of the same shape as the simple lower bound S of z modulo m to the n is at least 2 to the n times m minus 1 plus 1. So that's not the best known lower bound. I'll say something about that in a moment, but that's a sort of very, very simple lower bound you can get by a very simple construction. And the construction is literally just, if you look at this problem in z modulo m to the n, then you can take all 0, 1 vectors. So in other words, we take all combinations of zeros and 1s of length n, so all 0, 1 strings of length n. And for each of them, we pick m minus 1 different points in z to the n, which sort of have the prescribed sequence of zeros and ones as residues modulo m. Because as we said, for those points here, only the residues modulo m matter. So for example, for the string 1, 0, 1, 0, 1, 1, I can pick a point in z to the n, which has residue 1, where the first coordinate has residue 1 modulo m, the second coordinate residue 0 modulo m, and so on. And so I do this not just once, but for every 0, 1 string, I pick m minus 1 different such points in z to the n. That's possible, right, because there's infinitely many representatives of every combination of residue classes modulo m in the coordinates. And so now that gives me 2 to the n times m minus 1 points, and one can check that among those it's not possible to find m points whose sum has all coordinates divisible by m. So it's not possible to find m points whose centroid is a lattice point in z to the n. And so that means that number is not enough, and so we need at least a plus 1. So if all those details, I mean, we're a little bit too fast. Don't worry. My point was there is a construction which one can describe in roughly 2 to 3 paragraphs and check. And so it's really a relatively simple construction. There are some constructions which you do a little bit more, better, but which are a bit more complicated. And so I'll state those in a second. But the point is that already this very simple construction gives a lower bound which is roughly 2 to the n times m. And so this upper bound of 4 to the n times m is actually very good, right? Because it has the same shape. The only difference is the value of that absolute constant here. Okay. So, so let me also state what the beta upper bound was. So this beta lower bound. So this simple lower bound was improved to S of z modulo m to the n is at least m minus 1 times 96 to the n over 6, rounded down. And that's roughly 2 to the 1398 to the n times m. And that's for all odd m. And that's due to Edel from 2008. So basically, this lower bound, at least as long as m is odd, Edel improved this lower bound by finding a lower bound which is roughly, which have the same shape, but instead of 2, it has 2.1398 roughly. So that's to the n. But one needs to be a bit careful here. So it's up to a constant factor of that k comes from the rounding down here. So if you take n over 6 and round down, you may lose up to a certain number of factors of 96 here. I guess up to. So this 2.1398 is the 6th root of 96, and so you can lose up to roughly a 96 factor from the rounding down. And so up to sort of constant factors, these two things are the same. Okay, but so this means that the 2 here is clearly not optimal. It's not known what one should think is the optimal constant, but the much bigger problem is to even prove such an upper bound with such a constant here. Because A, there's the problem with the prime factor assumption, but the other thing is this was all for fixed n. And so basically, so I would say that for fixed n, this problem is now reasonably well understood. With a small technical caveat here about the prime factors of m. But if one now goes away from the range of fixed n and looks at this again, then it's still widely open what the right behavior is, yeah?
So there's a dependence in the behavior based on the parameter m, because when m is a power 2, we get just 2 to the n, but when m is odd, we get more than that.
Yes, so if m is a power of 2, then this is known exactly. It's this. And if m is odd, we have this lower bound, which is much more than that, right? Yeah. So really, so yes, you're right. So it's the parity or maybe the prime factors of m really do drive this behavior, and we shouldn't expect to, in general, just have like here, just sort of one nice affine linear function that's always exactly the answer. So we can't expect that, but if we are only interested in bounds, and maybe you don't care too much between 2, 2.13, or 4, then we could still expect that there is sort of upper and lower bounds sort of with different absolute constants that sort of work for all m and n. So basically if n is fixed and m is large, then this is pretty well understood. But if you look at, say, for example, the opposite regime where you fix m and let n be large, then it's wide open what happens then. And so that's the question that we want to sort of discuss today and next week. So basically, the main question we are interested in now is how large is this S of Z modulo M to the N for fixed M and large N. Okay, and so yeah, I mean, of course, it would also be great to understand this when both M and N are large. But typically, the first step should be with the two-parameter problem to understand it, what happens if one of the parameters is fixed. And only after you succeeded at that, typically, you can try to sort of understand it when both are growing. So that's also a very interesting question, what happens if both of them are variables. But since already this is very hard, we'll just focus on that sort of easier but still very hard question. Okay, so yeah, so basically for the rest of today and for next week, we are interested in trying to find bounds for this S of Z modulo M to the N for fixed M and large N. So the dimension N is large now, the number of points we want to pick is fixed. And so as we see in a moment, it essentially suffices to reduce to the case that this M here is a prime. And so we sort of make a formal argument for that in a second. But yeah, so really that means we can assume that this M is a prime and then N is large. And so if we've reduced to the case that M is a prime, then I guess we are in a problem in Fp to the N. So if M equals P is a prime, then this becomes Fp to the N. So we naturally transfer to a problem in Fp to the N, so sort of a problem over the finite field Fp. And so then we can remember the slice rank polynomial method that we discussed, and we can try to apply it to that problem. And so sort of whether that works and what's difficult about it and how one can go about these difficulties, sort of that's sort of the topic of today and next week. Okay, but so let's first sort of do this reduction to the case of a prime. So here's a lemma. So the lemma doesn't directly address the question, but reduce the question to the case that M is a prime. So the lemma is that S of, so if this M here is a product of two numbers K and L, then this S of KL to the N is at most L times S of ZK to the N minus 1 plus S of ZL to the N. Okay, and so that's valid for any K, L, N, so there's no sort of particular assumptions here. And so that's helpful in order, as we see in a moment, to reduce here to the case that M is a prime, but also actually in this proof of Allon and Dubiner, they also first use that lemma to reduce to the case that M is a prime when showing this, and then sort of plugging that back in, you then get it for all M. And so I guess similarly Zakharov sort of just focused on the case that M is a prime, and which is large enough with respect to N. Then he got this bound, and then he got it for free for the case that all prime factors of M are large. So basically, when studying this, using this lemma, you can sort of decompose M into prime factors, and then you basically only want to study the case where this number is a prime, and that's why here originally he just had the K. I mean, sort of in his main result, I think it's sort of for fixed N and a large prime, you get that bound, and then you get it for free for M with large prime factors. Okay, yeah, so let's prove that lemma. Okay, so this lemma states an upper bound for this problem where we want to pick KL points in terms of the upper bounds for the analogous problems where we want to pick K points or where we want to pick L points. Okay, so that means if we want to show this upper bound for S of Z KL to the N, that means we need to show that that many points, as on this right side here, are sufficient in order to always be able to pick KL many points whose centroid is a lattice point. So let's consider that many points. So consider a set S of L, so that many L times S of Zk to the n minus 1 as S of Cl to the n points in Z to the n. And so now our goal is to find KL points in the set S with a property that the centroid is again a lattice point. So we need to find KL points in S whose centroid is a lattice point. In Z to the n. Okay, so we want to find those KL points. But since what we are given here is in terms of this problem for K and this problem for L, so basically what we want to do is we want to sort of apply sort of this problem for K and this problem for L in order to, in the end, find these KL points. And so basically, we do this by going in groups of L points. So we first want to find some group of L points. So we have that many points. So that's in particular more than this, or at least this. And so that means we can find L many points in our set S, so that the centroid of these L points is a lattice point. First, we can find L points in S whose centroid is in Z to the n. So in our set S, just using that it's at least that many points, we are definitely, by the definition of this, able to find L points whose centroid, so that the centroid of these L points is in Z to the n. So after we've done this, we still have a lot of points left in S. So let's delete these L points. So let's delete these L points and repeat the process. So that means we delete this first group of L points that we found, we delete them, and now we look for another L points whose centroid is a lattice point. So then we delete them, and so we keep going. So in each step we find we find a group of L points so that the centroid of these L points is in Z to the n. So again, at each step, finding L points whose centroid is in Z to the n. Okay, so how often can we do this without running out of space here? So how often can we do this so that we are still able to apply sort of this, so that we still have that many points left, so that we know that we can find another group of L points. Indeed, after we've done it that many times, so S of Zk to the n minus 1 many times, we've deleted that many points, and so we still have enough left to do one more step. So after S of Zk to the n minus 1 steps, we still have enough points for one more step. So after having found S of Z to the this minus 1 groups of L points, so this factor here, we still have S of ZL to the n points left, and can find another group of L points. So that means after that many groups we can find one more, so in total we find S of Zk to the n many such groups. Okay, so in total that means we can find this plus 1, so basically it's this S of zk to the n many groups. So in total, we have found S of zk to the n groups of L points. So in total, we've seen that doing it for S of zk to the n minus 1 steps, in each step finding one group of L points, we can still do another step. So that means we have S of zk to the n groups of L points. In our set S, such that each group has its centroid in Z to the n. And these groups are all disjoint because whenever we found a group, we deleted the points from S. So we found that many disjoint groups of L points in S, so that for each of these groups, the centroid of the L points is a lattice point in Z to the n. So now that means we can look at, for each of those groups, we can look at the centroid, and that centroid is going to be a lattice point. So we have f of zk to the n different centroid points in Z to the n corresponding to these groups. So let's look at those points. Among these S of zk to the n centroid points, so these centroids are all points in Z to the n. So we have now that many points in Z to the n for those centroids. And so now among those, we can find k centroid points. So that, which have the property that for those k chosen centroid points, their centroid is also a lattice point in Z to the n. So in other words, we had that many groups. Each of those groups consists of L points, but now we are not looking at those L points anymore, but we are looking at the centroid of the points in the group, which is, by the choice of our groups, again a lattice point. So we have that many lattice points given by the centroids of those groups, and among those, now applying the definition of S of zk to the n, we can find k of those centroid points of the groups, so that of those k points, the centroid is again a lattice point in Z to the n. But now that means this centroid of those k points is now the centroid of the kl points in the k groups corresponding to these k centroid points. So each of those centroid points was a centroid of a group of L points. So we have k of those. So in total, that gives us kl points whose centroid we are looking at. So considering the corresponding k groups of size L, this gives kl points whose centroid is a lattice point in Z to the n. Right, so we had these k centroid points. They each were the centroids of this of a group of L points. We take these k groups together. So now that means we have kl points in S. And so these kl points in S, their centroid is now that centroid point here, because these kl points in S, they split into these groups of k groups of size L, and we can now determine their centroid by first taking the centroids of each of the groups and then taking the centroid of those k centroid points of the groups. And so that's then this centroid point we got here, which by the choice of those k points is in Z to the n. Okay, so the notation is a bit confusing here, but in short, by sort of, I guess, clicking it up that way, we are indeed able to find our KL points in our set S, whose center is the lattice point. And so that means this S was big for any set S of that size that we wanted to show as an upper bound for S of KL to the n, that indeed works. And so we have shown our upper bound for S of KL to the n. Okay, so that proof is done. Okay, so that means in this lemma we now had this upper bound for S of KL to the n. So in other words, for the Erdös-Ginzburg-Ziv constant, where this number m was a product of two numbers. And so applying this repeatedly for the prime factors of m, so in other words, splitting m into prime factors and applying this repeatedly, we can now deduce that S of Cm to the n for any m is at most m times S of C of P1 to the n plus and so on, plus S of C of Pj to the n, where P1 and so on to Pj are the prime factors of m. I mean, so in fact, this bound is even relatively loose because in fact, sort of the factors you get in front of each of those sort of is a product of the previous prime factors. But in what we want to do here, this doesn't matter at all, so we can just write down this looser bound. Okay, so in other words, that tells us if we are interested in bounding this Erdös-Ginzburg-Ziv constant S of Cm to the n for any number m, we can restrict to the we can find this bound in terms of these Erdös-Ginzburg-Ziv constants where we have the prime factors of m here, and then we only lose a factor of something like m here, which doesn't really matter in the regime we are interested in when m is fixed and n is large. And so that means we can basically reduce to the case that m itself is a prime. Because if we have a good bound for each of those terms, then we get a good bound for that term. So that means from now on we can reduce to the case that m is a prime. Yeah, and I also wanted to say each of those summands here, so each of those Erdös-Ginzburg-Ziv constants are at most that Erdös-Ginzburg-Ziv constant. So this number is lower bounded by any individual one of those terms. So really, if we don't really care about this factor m, and so then the sum, that's sort of, I guess, as many prime factors as m has another factor. If you don't care about those constant factors when m is fixed, really that reduces the problem to the case where m is a prime. Okay, so that means, so from now on, we consider the case where m equals p is a prime. Okay, so now we are interested in S of Zp to the n for prime p. And so, of course, S of Zp to the n, even if p is a prime, is still sort of defined in the same way. But the nice thing is now, if you're in the case where m equals p is a prime, we can sort of we can move away from that geometric problem and sort of translate this into a problem, into some additive combinatorics problem. So, and basically that's the following question. So let me sort of maybe first say that. So basically we translate that problem where m equals p is a prime. So this S of Zp to the n, we translate up to, again, some constant factor loss into a different additive combinatorics problem. So for a fixed prime p, S of Zp to the n differs by a factor of at most p from the answer to the following question. Okay, and so the question is this. The question is, what is the maximum possible size of a subset of fp to the n that does not contain p distinct elements summing to 0. Okay, so in other words, we are having, so this is an additive problem. The prime p is fixed, n is large. We look at fp to the n, and now we're asking for the maximum possible size of a subset. We can pick an fp to the n with a property that we do not pick p distinct points whose sum is the 0 vector. So let me try to explain briefly why sort of up to some constant factor at most p. This is the same problem as the Erdös-Ginzburg-Ziv problem about S of zp to the n. So I guess there's sort of two directions. So one is we need to basically find upper and lower bounds for this in terms of the answer to this problem. So maybe let's first start with let's first start with the direction that this is at least as big as the answer to this question. So indeed, given such a subset of fp to the n, we can choose representatives of each of the points in the subset. So each of these points in the subset is a point in fp to the n, but then we can choose a representative of that in z to the n. So we can choose representatives of each of the points in z to the n. So when we have such a subset without p distinct elements summing to 0, for each of these points in fp to the n, we just pick a point in z to the n, sort of whose coordinate residues correspond to the given point in fp to the n. And so now, among these chosen points, in z to the n, no p of them have a sum with all coordinates divisible by p. Okay, so by our choice of this set, in this set we don't find p points whose sum is a 0 vector. So that means after we lift the points into z to the n, we don't find p points whose sum has all coordinates divisible by p. But that means we don't find p points whose centroid is a lattice point in p to the z to the n, right? Because that exactly corresponds to the sum of the p points having all coordinates divisible by p. Okay, so that means if we have a subset of fp to the n with this condition here, then we can find a subset of points in z to the n of the same size, so that no p of them have a centroid in z to the n. And so, okay, so maybe let's write this. So no p of them have their centroid in z to the n, and so that means that's then a lower bound for this Erdös-Ginzburg-Ziv constant. So the Erdös-Ginzburg-Ziv constant is larger than the answer to this question. So now conversely, the other direction is maybe a little bit more interesting. So conversely, if we are given sort of an optimal construction for this problem, so if we are given S of z p to the n minus 1 points in z to the n, no p of which have their centroid in z to the n, then we want to find a large subset of fp to the n with this condition. So we want to find a large subset of fp to the n without p distinct vectors in it summing to 0. So maybe just as a remark, so this was defined as the smallest possible integer so that we can always find p points whose centroid is in z to the n. So that means by definition that if we take 1 point less, there is a construction where that's not possible. So we start with such a construction of S of z p to the n minus 1 point in z to the n, no p of which have their centroid in z to the n. And now what we'll do is we will project these points into fp to the n. So we can project the points to fp to the n so via the natural map from z to the n to fp to the n, just taking every coordinate modulo p. So now, when we do this projection, I claim that there can't be any p of the original points mapping to the same image. So there cannot be p of the given points with the same image So why is that? So if there were p points among those points here, which all had the same image, then that would mean that those p points project to the same point in fp to the n. So in other words, those p points have all the same remainder in the first coordinate modulo p. They all have the same remainder in the second coordinate modulo p, and so on. So that means their sum would be divisible by p in all coordinates. So otherwise, the sum would have all coordinates divisible by p. And so that's not possible because if the sum had all coordinates divisible by p, then the centroid would be a lattice point. And we started with here we started with a configuration of points where no p points have the centroid be a lattice point. So that means that's indeed not possible, and so that means there can't be any p points with the same image, so every image appears at most p minus 1 times. Okay, and so every image appears at most p minus 1 times, so that means there are at least, s of cp to the n minus 1 divided by p minus 1 different image points in fp to the n, and no p distinct image points sum to the 0 vector. So why is that? Why is that last point true? So why are there no p distinct points in the image whose sum is the 0 vector? But it's again via the same sort of relationship. So if there were p distinct points in the image whose sum was a 0 vector, that would mean that the p original points here, so those p original points, would have their sum have all coordinates divisible by p, but that's not allowed because then the centroid is a lattice point in z to the n. So that means that indeed, because in the original set of points there were no p points whose sum has all coordinates divisible by p, there can't be p points in the image whose sum is the 0 vector in fp to the n. And so that means we found a subset of fp to the n of this size with no p distinct elements summing to 0. So this is a lower bound for that question here. So the answer to this question here is at least this. And so in other words, S of zp to the n, this Erdös-Ginzburg-Ziv constant, is at most something like p times the answer to the question. More precisely, this is at most p minus 1 times the answer to the question plus 1, but so it's in particular at most p times the answer to the question. So this Erdös-Ginzburg-Ziv constant is indeed upper bounded by p times the answer to this question, as this argument shows. And so that means this is at least the answer to the question, and at most p times the answer to the question. So indeed, up to a factor of at most p, those two things are the same. And if p is fixed and n is large, then that factor of p doesn't really make a difference. And so that means really instead of studying this, we can now focus on that question. Okay, so that means since we wanted to study this S of the m to the n for fixed m and large n, we said we can first reduce to the case where m is a prime, but then we can reduce to this question. So this is really the question we need to study in order to study S of the m to the n for fixed m and large n. Okay. So this question is really the important question now. And so for p equals 3, this question above, so that question over there, is actually equivalent to asking for the maximum possible size of a subset of f3 to the n without a 3-term arithmetic progression. Okay, so for p equals 3, this question is what's the maximum possible size of a subset of f3 to the n without 3 distinct elements summing to 0. But now in characteristic 3 is the same thing to ask for 3 things summing to 0 or for a 3-term arithmetic progression. Because the equation in characteristic 0, the equation x plus y plus z equals 0, is the same as the equation x minus 2y plus z equals 0. So in characteristic 3, it's really the same thing to ask for a 3-term progression or to ask for 3 points summing to 0. And so that means the question that we care about now over there for p equals 3 is the same as the question of asking for a subset of f3 to the n without a 3-term arithmetic progression. And so that was a question we discussed a lot in the first 2 lectures in the series. And so we discussed that Ellenberg and Gijswijt proved a bound for this question of 3-term progression-free subsets. So Ellenberg and Gijswijt proved an upper bound of 2.756 to the n for this problem in f3 to the n. Yeah, so in the last 2 lectures we discussed this Ellenberg-Gijswijt bound more generally in fp to the n, but if you specialize it to f3 to the n and then calculate that particular constant we got in the bound, then that's what you get. So we have the Cp times p, where Cp was given by this by this sort of minimization expression. But if you plug in p equals 3, then you just get out a particular number, and so that's the bound you get there. And so, as we also discussed, their proof was rephrased by tau. So let's say it differently. It was rephrased via the slice rank polynomial method by tau. So Ellenberg and Gijswijt had this proof, and then a few weeks later, Chow reformulized and generalized this proof via what is now called the slice rank polynomial method, and that's what we saw in the previous lecture. So we saw this method, how it works, and specifically we saw it applied to this problem of three-term progression-free subsets of fp to the n. And so now that means that the slice rank polynomial method sort of gives this very nice upper bound for this question for p equals 3. But now a very natural question is, of course, what happens if you take p larger than 3? If you take p at least 5, can you still apply that proof strategy we saw last time and the slice rank polynomial method? Can you still apply that to that question over there for p at least 5? And in fact, we also sort of discussed this last time. So in fact, we had this question on the board in slightly different wording already in the previous lecture. So in the previous lecture, we said was the maximum possible size of a subset of fp to the n without a solution to the equation x1 plus and so on plus xp being 0 for distinct x1 to xp in the set. But that's the same as what's written here. So that's sort of the same question, just without sort of the equation with variables, just describing the equation with words saying summing to 0. So that's it's the same problem that we had on the board last time. And we had it on the board as an example for something where the slice rank polynomial method can't be applied, or at least where it can't be applied directly. So we saw it as an example of something where this approach we saw last time for three-term progression-free subset breaks down when we try to apply it for that. So let's write that down. But for p at least 5, the slice rank polynomial method approach breaks down. And the reason for this is that the natural tensor associated with this question is not a diagonal tensor anymore for p at least 5. Yeah, so because the relevant tensor is not diagonal. Okay, so we saw in the last lecture that in order to, the application of the slice rank polynomial method, in order to bound the size for three-term progression-free subsets of fp to the n, we wrote down a particular tensor, and then we checked that it was diagonal, and that allowed us to apply Tao's lemma, which said that diagonal tensors with non-zero elements on the diagonal have full rank. But here, the natural tensor associated with that equation won't be diagonal anymore, and that's precisely because of this distinctness condition. And so we discussed that in the last lecture, how this distinctness condition really, because of that, we lose control over the tensor being diagonal, and therefore we can't apply Tao's lemma. We don't have a lower bound for the slice rank anymore, and so that means this method breaks down. And so that means this sort of very nice approach for this question for p equals 3 doesn't sort of extend to larger p. Okay, but of course then still several people try to circumvent this obstacle and try to still apply the slice rank polynomial method to this question. And so in particular, the first person who did this was Naslund, who managed to prove a bound that the answer to this question, and therefore S of z p to the n, is exponentially smaller than the ground set size p to the n. And so he proved the following. Naslund 2020. Yeah, so as a preprint, this appeared in 2017, but published it was 2020 in the journal. So let P at least 3 be a prime. And if X is a subset of Fp to the n without P distinct elements summing to 0, then he proved that the size of X is at most 2 to the P minus 2 times Cp P to the n. And so here, Cp is the constant in the Ellenberg-Gijswijt bound for 3-term progression-free subsets. Of Fp to the n. Satisfying 0.84 is at most Cp is at most 0.92, and for sake of completeness, Cp was given by the following minimization. So Cp was the minimum over t between 0 and 1 of 1 plus t plus and so on plus t to the p minus 1 divided by p times t to the p minus 1/3. And so one can check that this is strictly less than 1. And so Ellenberg and Gijswijt proved that any subset of Fp to the n without a 3-term arithmetic progression has size at most Cp times p to the n. And so now what Naslund proved, so that was for the problem of 3-term progression-free subsets, which, as we just discussed, is a different problem than this problem, except if p equals 3, then they coincide. But so what Naslund proved is that also for that problem, if p at least 3 is a prime and x is such a subset without p distinct elements summing to 0, as in this question, then he proved an upper bound for the size of x to be at most 2 to the p minus 2, so some prefactor depending on p, times in the main term is now again Cp times p to the n. And since the Cp is strictly less than 1, this is exponentially better than the ground set size p to the n. Yeah. But so this base here is now roughly 0.85p. And so now, in order to do this, Naslund introduced a variant of slice rank. So as we saw, the slice rank polynomial method doesn't directly apply to this question. And so Naslund introduced a variant of slice rank, which he called partition rank. And so basically the idea of that variant was that in the slice rank, you consider, for rank 1, you consider factorizations of your function or tensor as a function of just one variable times a function of our remaining variables. And so for the partition rank, what Naslund considered was a function of some subsets of the variables times a function of the remaining variables. So he allowed any partition of the set of variables into 2 non-empty subsets, not just the set of size 1 and the rest. So basically, he allowed more possible partitions to be rank 1, and so that led then to a different notion rather than slice rank, which he called partition rank. And so with this partition rank, which he mainly introduced for this problem, he was then able to show by modifying this tensor in a certain way that it then kind of became diagonal, then he was able to show this bound. But a little bit later, Jacob Fox and myself noticed that there's actually a much simpler proof of basically the same bound, actually with a slightly better prefactor here. So we proved that So that preprint also appeared in 2017 as a preprint, so a few months after this. But then it was published a bit faster in 2018. And so we proved, again, that if P at least 3 be a prime, and if X is a subset of Fp to the n, which does not contain P distinct elements summing to 0, then the size of X is at most 2p times Cp times p to the n minus 1, which then can be upper bounded as 3 times Cp p to the n. Okay, so that means this bound is the same as here, except that the prefactor was improved to 3. Now, the improvement of this constant prefactor is not really important, but the main point was that we had a much simpler proof for this than Naslund's proof via partition rank. And the sort of our proof sort of deduced this from this Ellenberg-Gijswijt bound for three-term progressions, for three-term progression-free subsets as a black box. And now I should ask, so I'm already 4 minutes over the official original end time. When do I need to end? So I guess it's 12:04 now. Can I take 10 more minutes, or yeah, that's okay? Okay, yeah. So due to the interruption, so I wanted to present the proof of this. So deducing this from the Ellenberg-Gijswijt bound for three-term progression-free subsets in detail. Due to the interruption and the sort of that we are already now over the official end time, I just try to give a sketch. So I try to give a sketch of the simple proof that deduces this bound from this Ellenberg-Gijswijt result for three-term progression-free subsets. And then in the next lecture, I'll say more about what's known now about this question. So these bounds show that sort of this, the answer to this question here is at most the Cp times p to the n up to some prefactors. So it's exponentially better than p to the n. But the base of this bound here, this base of the exponent n, is still linear in p. So this is still 0.85p roughly here and here. So some much better bounds were proved in the meantime, and so I'll say more about this in the next lecture. And so I'll just finish this lecture by giving a proof sketch deducing this theorem from the Ellenberg-Gijswijt result. Okay, so here proof sketch. Okay, so the second inequality is easy to check. It just has to do with the fact that the Cp has that size. So we have to prove that first inequality. So we have to show that if X is a subset of Fp to the n without p distinct elements summing to 0, then X has at most that size. So suppose for contradiction that X is larger. Suppose for contradiction that X is larger than 2p times Cp times p to the n minus 1. So then let's do the following. For every element in X, let's count the number of three-term progressions where that element is the middle term. So for every element X in X, we count the number of three-term progressions in the set X, which have this particular small x as their middle term. So we count the number of pairs yz in X, but without this little x. So basically we count the number of pairs yz in the remainder of X after deleting little x with y plus z equals 2x. So that means y, x, and z form a three-term progression with x in the middle. So we count the number of such pairs. So suppose that for some X in X, there are at least p p minus 1 over 2 such pairs. So let's assume that there is some x, so that there's at least p minus 1 over 2 different such pairs satisfying this equation. Then I claim that x, let's give these pairs some names. So there are at least so many such pairs, and let's call them y1, z1, y2, z2, and so on to y p minus 1 over 2, z p minus 1 over 2. So then I claim that taking x together with all those points here in those pairs, so let's take x, y1, z1, and so on to y p minus 1 over 2, z p minus 1 over 2, I claim that all of these points together are p distinct points in x, summing to 0. Why is that? Well, why do they sum to 0? We have x plus y1 plus z1 plus and so on plus yp minus 1 over 2 plus zp minus 1 over 2. So this sums to 2x, right? Because this was one of the pairs with some 2x. The next pair 2, the next pair 2, and so on. The last pair 2, that sums to 2x. So this together is x plus 2x plus and so on plus 2x. So it's x plus p minus 1 over 2 times 2x, which is px, which is 0 in fp to the n. So indeed, all of those p vectors do sum to 0 in fp to the n. And you can also check that they're all distinct, because these y's and the z's were all chosen x without x, so x is distinct from all the other ones. And then those two must be distinct from each other, because otherwise all these three things would be equal. And then also you can check that not across different pairs you can get the same. So not an entry here can be in another pair, because then the whole pair would be the same. So yeah, for time reasons I won't go into detail, but it's now not difficult to check that indeed those are distinct. So we found p distinct elements in x whose sum is 0, so that's a contradiction of the assumption on x, so that can't happen. So that means that for every x in x, there must be at most p minus 3 over 2 such pairs. So fewer than this. So for each x and x, there are at most p minus 3 over 2 such pairs. So in other words, there are at most p minus 3 over 2 three-term arithmetic progressions in x with this x as their little term, as their middle term. So every point in x occurs as the middle term of at most p minus 3 over 2 of three-term arithmetic progressions. But that means in particular that we get a bound on the total number of three-term arithmetic progressions in x. So this means that in particular there are at most size of x times p minus 3 over 2 different three-term arithmetic progressions in x. So we get the total size of the number of three-term progressions just because every point occurs as the middle term of at most p minus 3 over 2 three-term arithmetic progressions. And so that means we know that the set x, we don't know that it has no three-term progression, but we know it doesn't have too many three-term progressions. And so now what we do is a subspace sampling argument. So we now want to modify the set x in such a way that afterwards we get a different set which has no three-term progressions at all. And in order to do that, we use probabilistic techniques. So we sort of do this in a randomized way, namely we consider a random n-1 dimensional affine subspace. So now pick an n-1 dimensional affine subspace V and Fp to the n, i.e. an affine hyperplane in Fp to the n uniformly at random. Okay, so we find this random affine hyperplane, so this random n-1 dimensional affine subspace, and now we intersect X with that subspace. So let Z1 be the number of points surviving in X after we intersect with that subspace. So Z1 is the size of the intersection of X with the subspace V, or in other words, it's the number of points in X which lie in the subspace V. And let Z2 be the number of three-term progressions in this intersection. So now, these are random variables and they depend on this outcome of this V. So this V is random, so these Z1 and Z2 are random. But we can calculate their expectations. First, the expectation of Z1, so that's the expected number of points in X lying in the subspace, where every point in X lies in this affine subspace with probability exactly 1 over P. So the expectation of Z1 is 1 over P times the size of X. On the other hand, the expectation of Z2, so in order to calculate that, we need to look at any three-term progression in X dot intersect V, in every three-term progression in X, we need to look at the probability that all three of its points end up in V. Well, the first point of the three-term progression lies in V with probability 1 over P. The next point lies in V with the subject to the first point lying in P. In V, the probability is actually already a little bit smaller than 1 over P, but it's roughly 1 over P. So in other words, for every three-term progression in X, the probability that the 3 points lie in V is less than 1 over P squared, because the first point lies in V with a probability of exactly 1 over P, and then for the second point, the probability is something like P to the n minus 1 divided by P to the n minus 1 minus 1 divided by P to the n minus 1, and so then you can calculate that's a little bit less than 1 over P. So every three-term progression in X lies in this V with probability 1 over P squared, and then the question is, or less than 1 over P squared, and then the question is, how many three-term progressions are there in X? Well, at most that many. We already calculated that. So this is an upper bound to a number of three-term progressions in X, and each of them lies in V with a or ends up being in V with a probability less than 1 over P squared. So we have this upper bound for the expectation of the number of three-term progressions in X intersect V, and so this we can say is at most 1 over 2P times X. So in particular, we see that if we combine those two equations, we find that the expectation of Z1 minus Z2 is bigger than 1 over 2P times X, right? Because we have 1 over P minus 1 over 2P, so we have more than 1 over 2P left. And so now, remembering what we assumed about the size of X here, that tells us that this expectation is now bigger than Cp times P to the n minus 1. Okay, but so that means that we can pick, so that means that this random variable Z1 minus Z2 is an expectation bigger than Cp times P to the n minus 1. So that means we can pick a particular outcome of this subspace V so that this difference is that big. So we can pick a particular outcome of V so that the difference between X intersect V of that size and the number of three-term progressions in X intersect V is bigger than this. Yeah. Thus, we can pick an n-1 dimensional affine subspace V in Fp to the n such that when we evaluate this, so we look at the size of x intersect V minus the number of three-term progressions in x intersect V, we get more than Cp times p to the n-1. Like we pick a subspace V so that this random variable is at least the expectation. So then this is bigger than Cp times p to the n-1. But so now, let A be a subset of x intersect V. So we pick that particular V. Now we look at x intersect V. So now that has this size. But now for every three-term progression in x intersect V, let's delete a point from that set. So let A be obtained by deleting one element from each three-term arithmetic progression in x intersect V. And so that means now what's the size of A? Well, we started with that size. For each of those progressions, we deleted an element. So the resulting size of A is at least this difference and is therefore bigger than Cp times p to the n-1. Okay? So we start with this set. For every three-term progression in it, we delete an element. So we delete at most that many elements. And so that means the set A that we are left with has size larger than Cp times p to the n-1. But on the other hand, by construction, A is a subset of V, right, because it was obtained from x intersect V. So it's a subset of V, but V is isomorphic to Fp to the n-1, right? V was an n-1 dimensional affine subspace. So V is isomorphic to affinely isomorphic to Fp to the n-1. And so A can be interpreted as a subset of Fp to the n-1, but A doesn't have any three-term progressions. Right, so A doesn't contain a three-term progression because for every we started with this set, and for every three-term progression, we deleted a point. So that means in this leftover set A, there's no three-term arithmetic progression left. So we find a subset A, which we can interpret as a subset of Fp to the n-1 without a three-term arithmetic progression, but with a size larger than this. And that's a contradiction to the Ellenberg-Gijswijt result. So this contradicts the Ellenberg-Gijswijt result, which for time reasons I haven't stated again, but we stated it in the last lecture, and maybe just sort of for recapitulation, it just said that in Fp to the n, a set without a three-term arithmetic progression has size at most Cp times p to the n, and so here we apply it with n-1, so we get Cp times p to the n-1 as an upper bound for the size of any set without a three-term progression, but here we have a set without a three-term progression which is larger than this, so that's a contradiction. And so maybe just one technical remark, so that that sort of affine isomorphism is very important, that preserves three-term progressions. So that's, that one needs to say. Yeah, okay, but so that finishes the proof of that bound, and in the next lecture we'll discuss what beta bounds are known for this problem. Okay, thanks for coming, and thanks for watching, for those who were watching the second half because of the interruption with the alarm earlier.